And now, please welcome to the stage, Dr. Jamal Molin.
Hi, my name is Jamal Molin. I'm from Northrup Grumman, from the Emerging Capabilities Department. I'm working on a number of DARPA programs. And so today I'll be talking about enhancing edge processing, and specifically imagers with in-pixel processors. So why are we talking about processing inside the pixel? Well, you can see here, imagine this autonomous car navigating about its environment. There's a lot of data that's being generated from sensors, and it has to navigate its environment, avoid obstacles, avoid accidents, and do this all quickly in real time. So there's a lot of data being generated, a lot of data to process. It's actually expected by 2025 that 465 exabytes of data will be generated per day globally. That's 465 billion gigabytes of data. So it's a lot of data to process, requiring a lot of processing power. So not only is large data being processed, but also there's applications such as UAVs, military applications where UAVs over contested zones have to actually have a computational need on the order of tens of teraops per second. So again, there's a lot of data being generated from these sensors and a lot of data to be processed. So why is this a problem? Well, moving data is expensive. So you can have a state-of-the-art sensor, a large format, a high frame rate, high dynamic range sensor that's expected to approach on the order of 100 gigabits per second, generating this data, but then it needs to get to the processor or get to memory. And moving this data is expensive. So you can have a high-end sensor, a very high-end accelerator like you see here, the GPU, FPGA. That's great, but you have to consider actually moving the data from the sensor to processing and to memory. This is called the von Neumann bottleneck. So we have to consider this because it's expensive. It's expensive in time and energy, and so we need to consider it when designing these systems. So how do we actually reduce the amount of data that needs to be transmitted from the sensor? So we can use what's called dimensionality reduction. And this is the idea of representing information from a high dimensional space to a low dimensional space. But the key thing is we want to retain the important information, the salient information. So this will allow us to still transmit data, the relevant data, transmit less data, and still maintain state-of-the-art accuracy of the overall task at hand. So there's different ways you can do dimensionality reduction. You can extract important features, or you can actually project the data, project these features from high dimensional space to low dimensional space. So it's important for reducing the amount of data to transmit and still accomplishing the overall task. So what's interesting is actually the brain does this. So the brain actually computes dimensionality reduction using visual saliency. Each optic nerve receives on the order of 100 megabits per second of data per optic nerve. So this is impossible for the brain to process in parallel in real time. So what the brain does is we actually compute visual saliency and devote our computational resources to only interesting or salient regions in the scene, and then do processing on only those regions. So we can learn from the brain and gain inspiration from the brain. And this is the idea of neuromorphic engineering, is to sort of bridge the gap between engineered systems and neuroscience. So going back to the hardware, so what we're doing on one of the DARPA programs in pixel intelligent processing is this idea of 3D stacking. And this allows us to do processing inside the pixel. So we typically have your detector layer, your ROIC layer, which has a shared time multiplex bus, and this is actually how data is transmitted, but this is where the bottleneck is. So instead, we have this third additional layer, a processor layer, where you can actually have low power analog circuits local to each pixel, and these circuits are doing the dimensionality reduction, and then you send less data off chip. And it's doing this in a smart way. And so while doing this, we're also maintaining low power. So our goal is to stay under 250 milliwatts per megapixel, reduce the energy delay product of not just the pre-processing on chip, but the system as a whole, because you're sending less data to the back end. And then again, the key is that we want to maintain the state-of-the-art accuracy of the task at hand. So So progress and impact. So again, we were working on that project, and also DARPA FENT, so fast event-based neuromorphic camera in electronics. And this program is built based on designing a 3D stack chip, but it's a sensor with in-pixel processing, but it's based on a neuromorphic sensor. So instead of outputting just traditional data, we're actually outputting events based on change that's sensed in the visual scene. And then we have in-pixel processing on that bottom processor layer, which actually filters out irrelevant events and then sends that data out for post-processing. So this is the idea. We want to leverage 3D stacked chips and also new materials as well, and be able to do this in-pixel processing. And we believe that this will truly revolutionize sensors and edge processing altogether. Thank you.